All right, then this is my second time recording this because like I fucked up my audio on the first time. So anyway, let's get started. So, nightmare pwn challenge. This is a hacked box challenge for the most part, and it's gonna take a while. Hopefully, I explain this to my best of my ability. So let's get started. So, the main things with this challenge is that we have a format string vulnerability. I'm not gonna go too over this real quick because I feel like I've done a lot of these problems in the past, but I guess for beginners, format string vulnerability is, for example, let's say you have a printf function that, in our case, it prints stuff out to the screen, and we are able to control whatever is being put inside that printf function in the parameter side. If we could control it and pass in percentage x or percentage whatever, for the most part, we could leak out stuff from the stack. That's basically it with format string vulnerability. So what we're gonna do with this format string is we're gonna do a GOTS overwrite. So what's a GOT overwrite for the most part? So with GOTS, GOT stores actual locations of libc. Libc contains functions such as get, printf, system, etc. And we could gain a coded execution that way. In this example that we have here, we have a buffer being passed into get, and then after that, it does a regular thing where it just prints it out, printf. So right here it says that there's a buffer overflow because of gets. It doesn't have a restrictions to it to how much we could put in, so we could put in more than 20 bytes, so more than the buffer has to offer. And also a format string vulnerability because printf in this example, we could pass in whatever we want. How usually you want to do a printf is like printf and then like a string saying what kind of type it's gonna be, like percentage s or percentage c, and then after that a buffer, passing in the buffer. But in this case, we just straight up passing in the buffer so we could control what we get to put in. And then right here, well, it says what we could do. We could use a format string to overwrite the GOT entry of printf. So we could overwrite printf with the location of system. And this was essentially change the code to this example that we have here. Gets, and then except for printf, it's system. So whatever we pass inside this buffer gets passed into system. That's basically GOT overwrite. We basically overwrite the functionality within libc. So let's go with the next one. So I guess one thing you need to know too is one gadget. So what are one gadgets? So one gadgets are simple like shell commands that is present in glibc. In this example, they're using exe cve, and this can be a quick win when you have GOT overwrite. So right here, for example, so except of yeah. And then the next time a function is called with one gadget is being executed, you could a shell is popped into place. So that's basically it for, like, I guess, the explanation part, and we can get started with this challenge. So with this challenge, for the most part, I guess I'll just run the checks because I'm not trying to do a check.py like every time. I already have like a soft script, but I'll use local. I'll do local.py. This one doesn't solve it. It just, yeah, this ignore this for now. I'll explain what this is for the most part. But we see no real raw. What does no real raw mean? So we'll just type in no real raw. Basically, no rel row, I guess. So relocation read only, which makes some binary sections read only. In this case, since there's no real row at all, that means that we could force an overwrite since there's no read protections only. So that means since there's no read protection, we could actually overwrite it. And then we have, I think if we look back, canary is found. So that means there's some type of stack canary. And X enabled, no shellcode. So I guess it's a hint, no shellcode. And pi enabled. So I guess pi enabled. So what is pi? Pi enable. Basically, pi stands for position independent executable, which means that every time you run a file, it gets loaded to a different memory address. And yeah, that's about it for the most part. So let's see. So luckily that means it's impossible to exploit. Pi executables are based around relatives rather than absolute addresses, meaning that while the location and memory are friendly random, the offsets between the parts remain constant. For example, if you know the function main is located at 0x bytes in memory after the base address of you somehow find the location, you simply subtract 0.28 from this to get the base address and from the address of everything else. So basically, we have to leak some type of address from this. So basically, we're gonna use a format string to leak an address, and then we're gonna like do the subtraction part right here. That's basically what we're gonna do, and I guess I'm gonna show you guys real quick. So If we pass this through Ghidra, and since, oh, I guess I didn't check what kind of file it is for the most part, so we'll do a quick check. But this file is mostly stripped, so it's gonna be a little bit harder than usually is. So you see, like, stripped. So that means when we pass it on to Ghidra, we're not gonna see like main or nothing. It's gonna be entry. So if we check right here, entry. So see, like, there's no main function or nothing. So if we click on the very first function, we have like 3 functionalities: 1, 2, 3, and 4. The ones that we're gonna look at mostly is 1 and 2, because that's where usually the string vulnerability is at, or the format string vulnerability is at. So if we click on 1, for example, we see that fprintf, we could pass in whatever we put inside this buffer. In this case, we could pass in 100 to local 128, which is 280. So this is fine. But right here, there's no check, so that means we could pass in whatever we want on local 128. So we could pass in like percentage %X or anything like that, and I'll show you guys later. And then the thing we have to look at too is the number 2 part. So number 2 right here, if we enter number 2, we get same thing again, but this time we're limited. We can only put in 6 bytes onto local 16, which is 6 bytes. But right here it's like printf, we control it for the most part. We could pass in whatever we want. I think another thing to look at is like, what is this doing? Because if we look right here, congrats, you escaped the nightmare, and it exits out right away. If you type in lol zk, I guess you could exit out for the most part. So well, I guess we'll test this out real quick. So let's just run this for the most part. We'll test out the string format vulnerability for both of these. So if you just run nightmare /nightmare. So what do you want to do? We'll check out 1, and then we'll just do, since we can control it, we could probably do %X, and we'll see a memory address pop out. See, look, a memory address just popped out. So that's pretty cool. Now if we do 2, %X, memory address pops out too. Now next thing I guess we want to check out is the exit functionality. So lol zk, I think, and then boom, we exit out. And I think if we try like 3, it doesn't even exit. Yeah, nothing exits. That's pretty cool. Now I've been talking for a while. So we know there's a format string vulnerability, and we know that there's a format string vulnerability with 1 and 2. So what are we gonna do right now? So what we're gonna do is leak out values from the stack using the percentage %P for pointers in hexadecimal format. So what we're gonna do is we're gonna try leaking values off the stack, and then just see what we could do. So what we're gonna do is first we want to be able to bypass pi. So we have to leak the address of some instructions. And what we're gonna do that, I guess before we do that, is first we're gonna disable ASLR. So simply we just type this command, echo 0t prop system kernel randomization via space, and we just type this, and then right now ASLR is disabled. So now I made I didn't make one, but I just copied it from a write-up that I was reading. So we'll just copy local fuzz.py. I'll do backhat. So what this is gonna do is it's gonna leak out values from the stack from the position from the option 2, and we're gonna leak out the values from this. So if I just simply run this, so python 3 local underscore fuzz.py, if I simply run this, we're gonna see values being leaked out for the most part. And then we see values being leaked out, and then we ask ourselves, what are with these values? So in the write-up that I was reading, for the most part, what it told was that from prior experience that this person that wrote it was that values that start with a bunch of 5s. So for example, I guess I'll show you guys an example. So one of these, they're usually values that are within the binary, and addresses that start with 7FFF7F are values inside, like for this one, for example, that come from glibc. And those that start with 7 F with a bunch of F. So example, like all these right here, where there's no 7 at the end, those are usually stack addresses. So what we're gonna do is open up giblibc for the most part. Oh no, not giblibc. We're gonna open up our GDB. Oh, I'm gonna be using the GEF version. So right here, I already have it open up, GDB Nightmare, and we have it right here. So what we're gonna do is simply I'm gonna type in start. Since there's like I told you, pi is enabled, so the addresses aren't fixed for the most part. And also let's see what else. I was gonna say something. My mind went blank. Yeah, the addresses are like yeah, they're not I guess fixed. So we type start. Now we see right here. You see how this is the starting point of this binary. And then we see this is a starting point, and this is an address within the binary. So I think if we simply just type X, and then we just simply type this, we're gonna see what this leaks out from binary. This is an address within the binary, so we should have access to this. So we type this XS lol zk. So this is an address with it. So it leaked out the address where lol zk is being held at, which is pretty cool. So now what we're gonna do next, for the most part, is check out these values from the binary. And the value that I'm gonna check out first is one that leaks out from glibc, because that's what we're gonna try to overwrite. So the one that I told you guys are usually the ones with a 7 FFF and then a 7 at the end. And the one that's very familiar to that one is this one, number 13. So I'm just gonna copy this one, and then I'm put it right here since I restarted the binary. So if I do X and then just put the library app right here, we see that it has libc start call main at plus 122. So keep this in mind. So now we have a few addresses of giblibc, which is this, and also we have the entry point of the binary, which is if you see right here where we started off right here, this is where it starts off at 555-180, because if we put start, it tells us the entry point right here. This is in GEF. It might be different in other like GDB versions, but I'm using GEF for the most part. So what do we do with this information? So I guess I'll go over my my local soft script and how I was doing it. So with local fuzz.py, oh no, I'll just clear this because I already have it. So what we'll do is try with backcat local.py. Okay, so we have here nightmare passing ELF context binary to ELF warn whatever. So we send in 2 and we pass in the value 13, which hold if you guys remember correctly, the value 13 holded this specific value of libc start call main, right? So I grabbed that value for the most part. You see libc start call main right here. Turn it to a hex, and it printed it out. It printed it out on my end. And then what I did is get a random address right here. Get an address from system. So I got an address. So I got the system address through GDB. So what I did was just simply type X and then system. And this got me the giblibc address of system. Now I subtracted these two values and either add or subtract, but in my case I had to subtract it. Oh, in my case I added them. So what I did was just or I subtracted these two values. So if I just go on I think I could show it right here. So Python 3. So I grabbed these two values. In this case, I think I grabbed libc system. because I think this one was, yeah, this one was a bit bigger. So I grabbed this one and just simply subtracted it from libc start call main, and I got this specific value from it, 15.150. And then what I simply did was just add it on libc start call main to get the address from system.gdb. So right now I'm printing out the system address. And then from what I did right here is I simply subtracted the system address from libc.so. So how do we do that for the most part is you simply just I'll exit out right here and do LLD and then nightmare. This is gonna link it to LDD. So what this command does for the most part, it tells you which libc it's this specific nightmare is using, and nightmare is using the libc located at this value. So what we're gonna do is we're gonna do a read ELF on S, and then we're gonna go do it on this value. This is gonna leak, and then we'll just do wide. I need to do this on my end. You might not need to do it on yours. And then I simply grab this, and then I just grep for system, or I grep for libc system. So I grep for this value, and then I got this specific value right here, 4C920. And by subtracting this, I was able to get the libc system base. So let's see if I can map this out for the most part. So I can, I guess, explain a little bit more. So right now I was able to leak libc start call main. And what I did was grab the libc system. This is how I'm thinking how it went. I could be wrong. Someone could correct me if I'm right or wrong. So libc system start call main and libc system. So libc or you get what I'm trying to say. Libc system. So initially I had this address. This is the address that I leak. And this is the address I got from GDB. I subtracted these two addresses for the most part. So I subtracted it and got like the difference value. And I added it to libc start call main. So now each time I run this program, I'm always able to get the system address from this. I'm able to get the system address. Now what I'm gonna do with the system address, or why I use the system address, is because when I was doing this at the beginning, I tried following the steps from the write-up. And the write-up, what they did was just simply they grabbed for whatever was leaked out. And for some reason, on their end, they were acceptive of it leaking out libc start call main. It was leaking out libc start main. The reason why I'm guessing, because this write-up was pretty old, is I'm guessing there was a recent change with libc where libc start call main, there was like a recent change on it. Like it happened, I guess, this year versus lib start. It was in this one. Libc start call main 2023. Start call main versus libc start main. There was a recent change that there's a recent change in like 4 months ago, or as 10 months ago. This was as 10 months ago. So this was a recent change on this on libc, where like they made a entirely new function for it. So that's why my values were a bit off when I was doing the write-up, and it took me a while to solve this challenge. So there was a recent change. So what they did, was just simply grep for libc start main. This is what they grep for. They grep for this, and they just simply grabbed this value. But in my case, I couldn't use this value for the most part because libc start main wasn't leaked. What was leaked instead was libc start call main. So I needed to leak this value. So since this value wasn't here on the giblibc version, which is pretty weird, I still don't understand why. I had to use a different value, and that's why I use system. So if I use this, nothing pops out. So I need to calculate a different function, and the function that I used was the system address, which was calling system. So yeah, I used the system one, and so like once I found like how far away libc start call main is from libc system, like the offset value, I was able to use it for the most part. And so at that point, that's when I use the system value, system, and then I grab this value, and that's why I subtracted its system address from the offset from the base. So now simply by subtracting the offset from it, I was able to reach so difference value. So now I'm able to actually I now know libc address now, libc system. But what I'm trying to reach is the base of glibc, because if I could reach the base of glibc, I'm able to like access any value. And how we simply do that is we just go and grep at libc and we grep for system, and this tells you the offset from base. So simply just by subtracting the libc system that we leaked by the whatever the offset value, which is this right here, minus that, I'm able to reach base of glibc, which is what I have right here. Libc base right here. And then after that, I just set that to my I just printed it out. And then after that I do a send line to. Reason for this is because we want to be able to leak out the base address of our ELF file. So if we look back closely again, exit Python 3 local fuzz.py, and then what did I leak out? 39. So if we go to 39 right here, you see that this matches to our entry point. We're gonna need this entry point later on, because see, look, if you see right here, we put start right here on I guess on Gef. We see that the entry point is located right here at value 39. So that's why I use 39 on my case when I'm using the local fuzz. So okay, now we did that for the most part. So now we know the base address of giblibc. So now what we're gonna do is if I run Python 3, which is local.py, we see that start call main gets leaked, system address gets leaked, glibc system, and ELF base address. So if I simply start GDB right here, GDB nightmare, we see that and then type start, and if I just type X for start call main, this value, we're gonna see that libc start call main, that gets called. So now we know that address. Now we want to get the system address, which is this value. So if I type X right here, we get system libc system giblibc base. Since it's all 3 zeros at the end, I'm pretty sure that's the base value. So if you just type this, right, X, so let's see, look, this should be libc, and then ELF base address, which matches our entry point. So these are the 3 main values we need to know for the most part. So what I need to do now is connect to the remote host. So in my case, what I'm gonna do is local.py is we're gonna connect to the the local host. So what I'm gonna do is comment this out and then just turn the comments on for this one, and then I'm just gonna connect to my remote location I have it on. So if I just simply delete this and add the new values, It might be, you might need to like turn on your instance for the most part. And then just do comma and then put in my port where it's at 3997 31397. And we'll do Python 3 local.py. We get different values for the most part. See, it's, you know how it changes now, because I'm guessing the remote one is using a different glibc from the one that my current system has. So I guess now we're asking ourselves, how do we solve this problem for the most part? So we know that glib system right here, glibc system right here is using a different one. So what we could do is copy these three values right here of start call main and use a site called to locate to find a matching glibc version. In my case, this one I had to go with the write-up because for the most part, I use libc bluecat.me, and with this one you're able to find specific versions of glibc just by copying the offset value. In this case, the offset value I'm going to use is 0b3, and then you write the function that you're leaking. And like I said before, this is where it became kind of iffy for me, because the value at 13 was start call main, but I'm guessing start call main is something new to I guess glibc for the most part. So what I'm gonna need to use is a different value for the most part, and the value that I'm gonna be using is libc start main. So what I'm gonna just type right here is just type underscore. This should fill it out. Oh wait, start main ret. I think this should find it. Let's see if I can copy this out right here. Copy libc start main. Find it. And then we get like a bunch of them. The one that we're going to use is the very bottom one, which is this one. It should be this one. Yeah. This one. We're going to use the very bottom one. The libc 6 2.31 Ubuntu 9. I guess this is the one. The very last one. We're going to use this, and then we're just going to download it. So this is the one that the remote host is using. And I already have it downloaded for the most part. So probably just click it and download it. And then see over here, nightmare patch, putting it. And what we're gonna do next is we're gonna patch the current nightmare binary using pwn-init. And I guess to show you guys what pwn-init does for the most part is pwn-init simply allows us to patch a binary with the correct version of libc, so we could have the correct binary, so it matches the binary from the remote host that we're connecting to. Simply what I did with most part is go to they have it right here. You could statically download it right here. So must libc. Wait, no, how did I download it? Oh, all right, I just went right here. I think right here. And then just download pwn-init right here. I just copied it and unzipped it right here. Yeah, but right here, and this is what you get. You get a binary called pwn-init. You might need to have you need to have these open SSL, libcm, and pk are required for the build to build this binary for the most part. And that's basically what I did. And I guess to show you guys for the most part what I did to patch this binary was simply type these simple commands of let's see, copy, paste, and this is what I got from the write-up from that I was reading before. So I'll just copy this, copy. So it'll be pwn-init and then the libc that you downloaded, and then you do bin and then the file nightmare and then no template. And right here you see libc. I already have it downloaded right here. Then you grab this and bin, and then the binary, and then template, and then if you just type it, oh, it's not gonna work on my end. Oh wait, it's a binary file, so dot slash, and then select fail patching binary because it already exists for the most part. But that's simply what you're doing. You'll get a binary called nightmare patch, which is patched with the latest. So right now, this patch binary matches the one in the remote host for the most part. So I guess we're gonna ask ourselves, what do we do after here? So simply, this is where we get to use a tool called One Gadget, which I explained to you guys what One Gadget is for the most part. So One Gadget is a tool for finding a One Gadget RCE remote code execution. You simply type on GitHub one_gadget. Pretty cool tool. You could probably use Gem to install it. And what you simply do for this challenge is just type one gadget on the libc that you're gonna be using. So I'll be using libc 6, the one that we downloaded. And then it tells us the one gadget addresses that we could use, which are these three. These are the three gadgets that we could use for the most part. And now what we're gonna do is add that to our I guess our new solve script. So basically, what we're gonna do is go clear ls, and now we'll check out our solve script. Bat solve dot py. Oh wait, bat cat solve dot py. So we have the same thing right here. We connect to remote host send to. We'll use 13 for the most part. Oh, and you see right here. So look, libc start main. So we use 13, the same thing as we did our local, but you see right here 13. Libc. I call it libc start main. Reason being is because it's a completely different part of it. So if you look at let's see, dot slash. Oh, I think you connect to it right here. So if I just simply type this and see, and I just simply delete this, and then if we just type what was it, 1, and then we'll just do percentage 13 $p. Oh wait, it's two, yeah. Percentage 13 $. What? Percentage 13 $p. It leaks out an address right here, but this address is if you look at, oh wait, I could just, yeah, I'm just like so tired right now, because if we look right here, so right now we're using the remote yeah, well, I'm like so lost right now, but anyway, I'll try my best to explain it. So anyway, so for now, this was nightmare. This was the binary nightmare, right? So this is nightmare. Now we're going to be using a different binary. The one that we're going to load up now is going to be nightmare patch, which is the patch binary that we used using the correct glibc version. So we'll just do gdb nightmare underscore patched. And if you type start, still starts at the same one, right? But this one's patched. And then if we do nano local.py, local, this is the local one, but this time we're gonna use a nightmare underscore patched. Python 3 local.py. Start call main. If I just simply copy this and just type X right here. Wait. Whoa, I'm so like lost right now. Oh wait. Oh, it's because I have AS. Oh, it's because I turned it. I'm like really dumb. I'm like so out of it right now. So anyway, exit. This is gonna be a long video. I need to turn off ASLR. I think it might come out a bit different this time. Hopefully. So now if we just type this, it should come out to something more that we used to. With GDB nightmare patch start. Hopefully. If not, then I'm just gonna look really dumb. I can't address. Damn. I might have done something wrong right here. Because I remember doing this. Nano fuzz.py. No, that's using that. Nano local underscore fuzz.py. Oh wait, it's nano local.py. Oh, it's because it's still, oh, yeah. So, local.py. And now we get addresses that we could use. GDB nightmare patched, and then if you just type X right here. Oh wait, start. And then we just type this string right here. So this binary nightmare patch matches the binary from our remote host. So we just copy this libc start call main X, and then just this value. We see it's libc start main. You see right here. So it was different from last time. Our 13 value gave us libc start call main, but in this case, in this patch binary, it's different. It's libc start main. So in this case, we're gonna have to recalculate our stuff a bit different, and that's what I did in my solve script for solve.py. So we just do cat solve.py, backcat solve.py. If we look at this, we see so we get 13 is libc start main, as I have right here, and simply what you do is just subtract it by 243, and that gets us back to libc start main. So now we're at libc start main, the base address of libc start main. But what we want to do is reach like the base address of libc, which is not that. We're at libc start main. So after we do subtract 243, which is from right here, this is where we get 243 from, and this is 243 right here. What we want to do is simply do the read left thing, but simply from what we did from last time. So if I copy this and just exit out right here, and then just do this. Oh wait, read left from libc.6, so it'll be this. We get 26F70, and we simply subtract that from that too, and then we get our base address of libc, which is pretty easy because before, like I said before we were leaking start call main, but start call main didn't exist, so I had to like get another address, which in my case I use system, but in this case, since lib start main exists in glibc, it was a lot easier to do. You didn't have to get another function address. So yes, like if you type this, it's not there. Pretty weird, huh? And libc, I guess a question you guys might ask yourself, where did I get libc.so.6? That was basically from after you do pwn init, or after you do the whole pwn init thing, which is to like patch the binary. You could either use this or this one. It doesn't matter for the most part. I'll show you guys. It won't really matter. Oh wait, libc start main. And I'll just replace this value with they're basically the same thing. This is the one that after you patch it, you'll get this one, but you can use either or. So if I just copy this, copy, same thing. See, look, same thing. So anyway, after that, I get the base address, and then after that, what I want to do is get the get the ELF entry point. Same thing like I said last time. The entry point was not that hard to find for the most part. This time it was at 20. because after you patch it, the addresses get like mixed up. Because I was using like I guess my version of Kali, that whatever libc it comes with. But like after you patch it, you're gonna have to rerun the fuzz and check out where it's at. So I think if we fuzz this again, if we go on nano local fuzz.py and then just change this to context binary context binary.process patched. If it's on Python 3 local fuzz, we see that what 20. I guess 20 now holds. See, like 20 now holds it. Before it was what 39. Now 20 holds it because after it's patched, the addresses get messed up. But in this case, it went lower, so it was more in our favor. So we yoinked 20 and then we subtracted by OX1180. So I guess you're asking yourselves, how do we get this value? I simply got this value from Ghidra. So if you go on entry point, you see that process entry right here. Yeah, let's go on entry. So this is the entry point where it happens, entry, and then this is the very first value. That's basically where I got it from, 1180. Basically, or you could grab it from also from if we go right here. If you go right back right here, I think I have it on my soft script. Oh, basically right here. You can also get it from obj dump or Ghidra. So if you just go right here, I'll just copy this. The .text section, it just tells us where the binary starts executing, and then see like 1180. You subtract it, and then you get the base address. And then simply right here, you want to pass in your one gadgets, the one gadgets that that you found by simply typing one gadget and then gadget and then libc dot. So you pass in these three values that you get from right here, and you just pass in one to see, I guess, to check. And then after that, what we'll do is do a string payload. So with this case, FM string payload, we it was like one of our other binary exploitation challenges in which we found where when we do a format string vulnerability, we want to check where we control the stack. In our case, if we just run nightmare on not nightmare patched, and then we type in 1, and then we just do percentage lx dot, and then we just copy a bunch of this time, a bunch of this. We see that eventually after the, let's see where, so this is 1 2 3 4 5, no, is it 0 1 2 3 4 5. Oh wait, I think I might have done this wrong. Simply, oh wait, I think I got it right here. If we just type exit, because like after this, because copy and then just go right here. Oh yeah, exit, because I didn't press 1. So if you see right here, 1, this is a value off the stack. 1 2 3 4 5, and after the 5th value, it seems to be the same after the 5th value. Reason being, after the 5th value, we control, if you, I guess, dehex this, dehex, and just go to like a hex to string converter. And if I just show you guys, see, look, this is one of the values that I got from the string that was repeating. Is basically lx what we passed in. So at that point, we know where we control LX, which is the 1, 2, 3, 4, fifth value. So that fifth value, and that's how we got the fifth value right here. And then what we want to do is replace the got exit, because if you guys remember from the binary right here, Ghidra, if you go to entry and if you go to when it enters 1, oh no, is it, yeah, no, when it enters, oh no, 2 2, yeah. And when we write congrats, you escaped this nightmare, and then you exit, and you know how var1 needs to be low zk. So once we enter low zk, go right here on var2. If this is low zk, it says congrats, you escaped this nightmare, and then you exit out. What we're gonna do is replace the exit value of it, the glibc. We're gonna replace it with the one gadget, which is gonna spawn our shell, and it's gonna save in the payload, because right now we did a format string vulnerability on number 1, because that's how we do it. And then after that, we're just gonna exit out, and then when we type low zk, it's gonna print out our line saying that congrats, you exit out. But except of exiting it out, is gonna get the shell. So if we simply just is this gonna do it on our remote? Yeah, it's gonna do it on our remote. So if you just type python 3 solve.py, we see base address, we see our shell, and then boom, we have a shell. So we type ls, we got cat flag.txt, and we get hack the box, are you awake yet? So let me see if I'm still signed in, because I don't want to like leak my hack the box thing. So submit flag. Hopefully, I've been doing this for like what, 45 minutes. That's crazy. Oh yeah, I need to sign in again at my hack the box. That's funny. But yeah, that was about it for this challenge. Oh, wait. I don't think I need to sign in. So I just type this in, 5, submit, and I think it's submitting right now. Oh yeah, submitted. So I guess I'll show you guys. Yeah, Pwned. So yeah, that was about it for this challenge for the most part. So yeah, we used, I guess I'll explain this last part again. So after I guess this whole part, we're just leaking the addresses for the most part, and then this part we set up our one gadget, and this is how you set it up for the most part. You get the 3 addresses that you get from your one gadget. Get your 3 addresses, put them inside this right here, and then you run fm string payload, which is like a shortcut, makes it a lot easier for you. Find where it repeats. In our case, it was at 1 that you're able to do it, because like if you press 2, if you guys remember correctly, 2, you can only put in you can only put in a max of size 2. Oh, this is fun. Entry libc right here. We check 1, 2. You can only put in 6 bytes onto the 6 bytes. So that's why we couldn't use 2, and we had to use 1. If you go back to entry, and then with 1, you're able to put in 100 bytes of memory to this 280, which won't cause a buffer overflow. But since it will cause a string F vulnerability, since we get to control what's being put inside the sprintf. And then after that, you need to find where it repeats, so you could, because at that point you're able to overwrite it. And what you need to do is add the glibc address, and then after that, put the gadget address to replace where the exit address is at. We send in 1, we pass in our payload, and after that we just want to exit out, and the only way to exit out is by using lolzk. We type lolzk right here. Hit me up. No, that's not printf. So we go entry function. You enter 2, right? No. Yeah, you enter 2. If it matches, because this is gonna check if it's lolzk. If it matches, it prints out congrats, you escaped this nightmare. And then after that, it's gonna exit. But in our case, since we overwrote exit with a shell command, or with a one gadget command, it gives us a shell instead, and that's how we got the flag for the most part. So anyway, that was about it for this challenge. This is probably gonna be my longest video ever so far. Pretty fun challenge. I learned some new stuff today, and yeah, that's about it for this video. Hopefully, guys, I didn't confuse you guys any more than I was supposed to. But yeah, anyway, that's about it. Peace.